cosine u times all of this junk down here. I'm going to run out of room. Let me do it here. Minus sine n minus 1u cosine u minus integral negative cosine u times n minus 1 in parentheses sine to the n minus 2 of u times cosine u times du. That right there is the diagonal, yeah? Okay. Let's talk about constants. Can I pull any constants out of this? You can pull the negative out. N minus 1 is a constant. Pull that out. So this becomes negative sine to the n minus 1 of u cosine u plus n minus 1 in parentheses integral sine to the n minus 2u times cosine squared u du. So I just put my cosine and my cosine together, cosine squared, put the sine to the n minus 2 of u here. That's the same thing, right? Is that the formula? I should have written the formula down over there. I didn't, though. The formula is negative 1 over n sine to the n minus 1 u cosine u plus n minus 1 over n integral sine to the n minus 2u du, I think. Pretty sure that's what it was. Just double check it. Yeah, okay? That's what I'm trying to get to. So what, are we off on anything here? Like negative sine to the n minus 1 u cosine u. I almost have that, don't I? The only thing I'm missing is a what? The n on the bottom divided. I'm missing the 1 over n. I have the negative. Over here, I've got an integral with n minus 1, but I don't have an n on the bottom. And the most important thing is look at the integral itself. The integral itself doesn't have a cosine in it, right? This one does.
So do you change the cosine squared to the 1 sine?
It's exactly what you do. You take cosine squared u, use a Pythagorean identity, and you replace it with 1 minus sine squared u. We all agree that that's the same? So if I rewrite this, I think I'll go up here to do it. I'm going to replace that with 1 minus cosine squared u, but I'm going to rewrite everything. Minus sine to the n minus 1 u cosine u plus n plus, no, n minus 1. Minus 1 integral sine to the n minus 2u times parentheses 1 minus sine squared u. That's a definition of cosine squared from pre-cal. Yeah? Now, distribute this through the parentheses. When you distribute that through the parentheses, this times 1 is itself, right? Okay, I'm going to have two terms here. So sine to the n minus 2u, that's this to this. And what about this to this? Sine to the n. Because you're adding exponents, right? You're adding this exponent to this exponent. N minus 2 plus 2 is just n. So that's just going to be minus sine to the n u, close it off, du. Y'all okay up to that point? We're getting close. Getting real close. I'm going to write the next line, and then you can tell me what I did. What did I do there? I split this into two integrals, right? Because it's subtraction, I can do two different integrals on this. And that n minus 1 was in front of the integral, so it's got to go to both. So I put the n minus 1 in front of that in an integral, and then I did the n minus 1 in front of that in an integral, but it was subtracted. Good? Do y'all see what I'm doing now? What am I going to do now? What?
You're moving it to the other side.
This is the original problem over here, isn't it? So we did this one time. It was that problem that we did with the e and the sine together. It like appeared on the other side. This is appearing on both sides. So I'm going to undo this on this side by doing what? Adding how many of them? N minus 1 of them. I'm going to add n minus 1 of these integrals to this side. Pardon?
Why is the n minus 1 still on here if you moved it again?
This right here splits into two integrals, doesn't it? It'll be this integral minus this integral. But this n minus 1 is supposed to apply to everything in there. So if it goes into two things, the n minus 1's got to go to the first one and to the second one. It's like if this was a 2, you would distribute the 2 in front of both of these.
But it still stays in front of the whole problem is what I'm asking. Even though you already distributed it, I thought it would go away.
I distributed it into, how I can explain. This right here, right? That right there can be split up into two integrals. This, I know this is very small, du, minus the other integral sine to the nu du. Right? Just what's in purple can be split into two integrals. But all of that had to be hit with this. So that n minus 1's got to go here and here. Yes?
But when you distribute it, doesn't that one go away though? The one in front of it? So I'm asking. Like the n minus 1, should it be there still even though you already distributed it?
Yes. Well, I'm trying to think of something. What if I did this? Like if I had 2 and then in parentheses x minus y, right? When you distribute this, it's going to be 2x minus 2y, right? The 2 is still in front of this one and in front of this one. So the n minus 1 gets distributed to this one and this one, so it's going to be in front of that integral and in front of that integral.
Oh,
It's in front of both.
I see what you meant.
Do you see it?
I thought that was the one inside with the first integral. That's why.
Oh, you thought this was in here with this one. Got you. It stops at the end of du.
Oh.
At the end of du, it separates to a separate term.
Okay, that's
See it?
where I was confused, yeah.
Okay. Good question.
Sorry.
No, it's a great question because those are those little subtle things in the notation that you have to be clear on. All right, so now I'm going to add, right? I'm going to add this to this side. If I do that over there, I've got to do it over here. I'm going to add n minus 1, sorry, of these integrals. Over here, good news. It's all gone, right? All right, so it's going to stop right there. But on that end, how many will I have? N of them. And the way we get n is, you imagine that there's one of these integrals, right? One of those, one of these, and n minus 1 of these. So if this had said 1 and 3, you would just add them together, right? But it's 1 and n minus 1. Add those together. 1 and n minus 1, that's what? N, right? So we're going to have n of those integrals. Moving on to the next line. So I'm going to have n of these integrals. Can I just write it right here? N of those integrals is equal to all of this, right? But with this gone. So I'm almost there. I think some of you probably see it now. What's the last step? Divide by n, right? This is n of these. I just want to know what one of them is. So divide this by n. Divide this by n. There's two terms here, so I'll divide that by n, and I'll just divide this thing in front by n. And do you see if you do that, you could just really write this as a 1 over n out front, and this would be n minus 1 over n. So there it is. That's how we generate reduction formulas. I believe that there are two homework problems like that. If I'm not mistaken, hold on. Let me just double check. 35 and 37? Yeah, 35 and 37 are reduction formula problems. What do y'all think of that? Beautiful, exactly, that's what I was thinking. It was beautiful. So if you're like a math major, I don't know, I think I might have a few math majors. Like if that stuff doesn't get you excited, nothing really is ever going to get you excited. That's us creating a formula that's in the back of the book that people would normally look at and go like, what the heck, how'd they come up? Well, that's how. It might have been found in the cave. Maybe that one.
What number formula was that?
That was formula 73. All right. That wraps it up for integration by parts, 6.1. Y'all feeling good? Got about 30 minutes left. All right, so we're going to talk about 6.2. Before we do 6.2, a couple of things from pre-cal that we're going to need. We should all be very, very clear about the Pythagorean identities. I know that we've seen that before and we've used it before. Just remembering that you can solve this for sine squared. We just did that a little while ago, didn't we? We had actually solved for cosine squared. Right? So be aware that those two formulas exist. They are both generated by just manipulating the first one. And then there's also some formulas in pre-cal. These were called the I believe it's the half angle identities. It's on your sheet. I call them the power reduction formulas, but may I? Mm-hmm. This is on reference page 2, bottom right-hand corner, half angle formulas. I don't like the name, okay? But this is what it is. It says if you have sine squared x, that this turns into, the formula the way it appears there is this, 1 minus cosine of 2x over 2. Does that look familiar? If you have sine squared x, you can basically get rid of the power. And it's going to convert into something that will not have powers anymore. But what you give up here is that you're going to have to make the sacrifice of doubling the angle of whatever was in it. And you have to use that formula. Now, I don't like that formula for what we're going to do. So what I do is I factor the 1/2 out. And when you see me use that formula, that's the way I'm going to use it. So I just pop that 2 out of everything. And it's really, if I distributed that back through, I would get this. Okay? It's called a half angle formula on your sheet. It's called, in my mind, the power reducing formula. You reduce the power. Cosine squared x is almost exactly the same as this one. Anyone know the difference? It's plus between them. And it is still cosine, all right? So it doesn't even switch. Like here, it's sine squared and it goes to cosine 2x. On this one, it's cosine squared and it still goes to cosine 2x. But it's a plus in between. Okay. Be aware of those.
Why does it stay cosine?
That's just the formula. I mean, again, we could sit here and say, well, you know, is that same? I think it was the cave right next to that other cave where they found this one. I mean, this can be derived, right? This could be derived. Yeah, it's a cave system of math formulas.
Natural bridge
we
calculus.
can't take, unfortunately, we can't take the time to go back and derive all these formulas, but there is a derivation. I guess I could do one thing to convince you that it's true. This is kind of a cheesy way of convincing you, though. If I took this and added this, what should I get? If I take that and that, I should get 1. So if I take that and add it to this, I should get 1, right? So let me write it this way. 1 minus cosine 2x over 2. That's sine squared. If I add the other one, this one, like that, right? They already have a common denominator, so I can just put them together And 1 plus 1 would be 2, and then this one cancels out. So it's 1, so that should make us feel better, I guess. But, you know, that's no way of proof. It's just making us feel better about it. That would be one of those trig identities. You know, back in pre-cal, we were like, you know, prove this trig identity. You start with one side and you turn it into the other. All right, keep those in mind. Now, that formula 73 is very nice, wasn't it? The one we derived. And we could use it for a lot of different things, including this problem right here. Oh, I should introduce you to this section. Oops. This section is titled Trigonometric Integrals and Substitutions. So there's really like two main parts to this section. The first part, trigonometric integrals, is integrals that involve trig functions in trig functions alone. So sine and cosine and tangent and secant and all these different things, where that's all you see in your integrals, are just trig functions. How do we attack those? And then the second part of this section is what we call trigonometric substitutions. So that's going to be a really cool part of this class, and it's not going to be on this test, and just for now, don't even think about it. Just realize that there's two major parts to this section. We're going to do a little bit of this first one today. We won't finish it. We're just going to touch on it a little bit. And we can read through those notes, but I thought since we're just touching on it, it would be better if we just kind of go after a few problems. So let's go to this one. Yeah, I'm gonna take attendance today off of your quizzes. So if you didn't take a quiz, just make sure you talk to me after class that you were here. Could we use formula 73 on this? Yes, okay, but we're not going to, all right? We're going to do it using just our knowledge of trig integrals. So I want you to realize here that we have an odd power, right? Odd number. Anytime you see an odd number on sine or cosine, you're going to do the following. You're going to peel off one sine. So if that was sine to the 5th power, you would have peeled one sine off, and this would have been sine to the 4th. If that was sine to the 7th power, you would have peeled off one sine and left it as sine to the 6th. Understand? It's always going to be an even one, and then the other piece would be just sine, right? Now, with this in mind, we know that this piece right here is the derivative of what? This is the derivative of cosine, isn't it? Well, I mean, off by a negative, but yes. If I had cosines over here, then I could let u, basic substitution, right? I could let u be cosine, and then its derivative would be here. So the question is, can you turn that into a cosine?
Yes.
Absolutely. 1 minus cosine squared. So I'm just going to rewrite this now as 1 minus cosine squared x sine x dx. And this is not integration by parts. This is a basic u substitution. My u here will be what? Just cosine x. Just cosine. While I've got this on the board, I want to point something out that I saw quite a few people do on the previous quiz, not today's, and that's